I'm actually hoping you've heard of a buffer solution. So, what is it? How would you describe a buffer solution? So, we can say a buffer solution is basically a solution that resists the change in the pH. What it tries to do is it tries to somehow maintain the pH within a certain range. Okay, so the basic idea is if you have a buffer solution, let's say this is our solution, and then it has got the pH of let's say 8, and then we decide to add, let's say, a strong acid. So we do know that a pH below 7 tells us to say something is acidic. So we expect that after adding a strong acid, our pH is supposed to be lower, somewhere to 2. Okay. Now, when you get to do that, adding that strong acid to a buffer solution, we basically don't expect a change in the pH. There may be minimal changes. Let's say the pH gets to drop to, let's say, 7.98. So such a solution which is resists changes in its pH is what we call a buffer solution. Okay, so now we need to understand what a buffer solution can consist of. Of course, we now understand that this is just going to be a solution that is resisting changes in the pH. Okay, so it can be made up of a weak acid, and then a weak acid with what? Its conjugate base. Okay, so when you have a solution made up of the weak acid itself and then its conjugate base, then you do expect that to be a buffer solution. Let's try to look at an example. So we all know that when you talk about this weak acid in that form, what you'd expect is after dissolving it in water, you expect the formation of what? You expect the formation of its what? Of its conjugate base, which is going to lose what? A hydrogen. So that it will be a negative. And then we expect the formation of the hydronium ion, something like that. So this is our complete equation showing the dissociation of this acid and then giving us that conjugate base on the other side. So now, what you might expect in a buffer solution is the fact that you're going to have in your solution is going to consist of the acid itself as well as what? As well as the conjugate base. Okay, that's what you need to expect. So now that conjugate base may be connected to something, let's say maybe a metal, maybe sodium. So this is a possible combination that we can have in our solution. And in our solution, we have the acid itself as well as a conjugate base. So when we get to add, let's say we decide to add a base, or maybe we can even talk about an acid. If we decide to add an acid to that buffer solution, we do expect our pH to be lower. But what is going to basically happen is the fact that the acid is going to react with the conjugate base. That's the way it works. So the acid will react with the conjugate base, and that is what is going to prevent the decrease or the presence of the hydronium or the hydrogen ions in our solution. So therefore there will be minimal changes in the pH. Okay, so we can also have a combination of a weak base with a conjugate acid as well. That is also another form of a buffer solution that we can have. And of course, we have got two different kinds of buffers. We have acidic buffers and alkaline buffers, of which I think I've already talked about them in the two scenarios or the two kinds of solutions that I've talked about. A case where we have the weak acid, and so if you have a weak acid, and then you also have its conjugate base, that's an example of an acidic buffer. Okay, and then also, of course, we do expect the pH of such a buffers to be what? Below 7, because anything below 7 is acidic in terms of a pH. And of course, alkaline buffers, this is relating to having a weak base and then combined with its conjugate acid. Okay, so that kind of combination gives you an alkaline buffer, because you expect the pH to be greater than 7, which is denotes alkalinity. Okay, so now we do now understand the formation of a buffer solution and basically what a buffer solution is. Okay, so how do you get to prepare a buffer solution? Okay, so what is very, very important for us to understand is how we get to now determine these very, very small changes in our pH when we have a buffer solution. So knowing that we do expect to have the weak acid as well as its conjugate base, how do you get to now find the pH? Okay, so the equation that we get to work with to find the pH for buffer solutions is called Anderson. Okay, so Anderson-Hasselbalch equation. So it is a very, very simple equation that comes from the very, very basic idea of the fact that in a case where you have an acid, okay, let's say HA is our acid, and then we have it being dissolved in water, and then what we expect to be produced is we'd expect the proton to be there, and then to also get to have something being produced there. So let's try to name what we have. So on the left hand side, something attached to the hydrogen is referred to as our weak acid, and then of course this is water, and then what we expect, this is a proton, and then the air is obviously going to be the conjugate the conjugate base. So this is what we have in our equation. Now, under a normal case, how do we get to find the Ka expression for this acid that we have? So the Ka expression for this equation that we have is of course going to be dependent on the products. And of course you need to pay attention to the states. This is in aqueous state, so only water is going to be in liquid state. And then we do know that liquids and solids do not appear in the Ka expressions. So we therefore expect that we should have our our protons, and then our conjugate base, which is denoted by A in this case. And of course this is just something that I'm using to represent the actual acids. For example, if you talk about the case where we talked about this acid, okay, talk about this kind of an acid, you do expect that after dissociating in water, it's supposed to be something that is going to be something like that. So the basic idea is I'm representing this entire part by a letter A, okay, so that it makes more sense. So that it is HA, and then the other side you lose the H, so that it just becomes A minus, and then the proton is also denoted. So that's just something that I'm trying to use to make it easier, so that it can make more sense. And then of course we expect to divide by our reactant, which is our acid itself, which is basically HA. Okay, this is what we have. Now this is where we are going to come up with our equation that is going to help us to find the pH every time we are asked to find the pH. So with the knowledge that we have of our logs, we are going to take the negative log on both sides. So negative log of our Ka, and then negative log of this other side as well. So let me try to just create some more space so that we can have negative log of this as well. So from our logs, what do we know? So from our logs, we do know that if you have the log of two things being multiplied, let's say the log of A and B, that is the same as what? Log A plus C, log of B. So multiplication, you can split them as addition, and then of course if you talk about division, you can split them as what? Subtraction. So that's the same as log A minus log C. So we apply those simple rules to what we have. And of course, you need to understand at this point that there is something that is very important. Every time you have the negative log of Ka, what do you expect? What is it, what is that called? So this is basically called pKa. Okay, so pKa is basically the negative log of Ka. So I'll write that, and then is equal to. So we'll try to split what we have on our right hand side. How are we going to split that? So what did we say? So we said, if you look at multiplication, you basically think of so I'll write that negative log. Multiplication, you think of addition in terms of our logs. So first of all, I'll consider the proton to be separate, and then of course I'll consider that conjugate base that we have to be divided by Ha, okay, which is our acid itself. And then as we get to go down, what do we expect? So we can now split that. Well, we do know that our pKa is going to be equal to, so the negative log of that can be separate, and then of course we've split it, and then the other side can be together now, A over Ha. Okay, this is the form that we have. Now at this level, I do understand that we basically understand the fact that whenever you're talking about the negative log of the proton concentration or the hydrogen concentration, that denotes your pH. So we have a pH and then minus log. So from what we had written from our equation, if I go back to our equation, we had Ha, which was our acid. Of course, we had it being dissolved in water, so that we had A minus, which is basically our conjugate base, and then of course we also add a formation of what? A proton. Okay, so in this case, the A minus that we have is basically representing what? Is basically representing our conjugate base. And of course, we did mention that that can be connected to a certain metal, and of course in most of the cases that is going to form a salt. Okay, so for example, acetate ion, sodium acetate, so all those things can be salts. Okay, so we can either represent A to be a salt, or we can just say it's a base. Okay, so we can consider it to be a base, and then we'll say divided by what is on the bottom. Of course, Ha is our acid there. So let's think of it as a base. Of course, take note it's a conjugate base over the acid, so that you know that this is the equation that you are going to be working with every time you're trying to find the pH of what? Of a buffer solution. And of course, if you try to make the pH to be the subject, you do expect that it's going to be the addition of the pKa plus what? Plus the log of your base, of course your conjugate base, divided by the acid. Okay, so this is the equation that we are going to be working with to perform our calculations when it comes to the pH of a buffer solution. And of course, I do believe we now understand what a buffer solution is. And let's look at one practice question to just help us understand how we get to apply this equation to approach our questions. Okay, so the question says a buffer solution contains 0.384 molar concentration of that, and then 0.239 molar concentration of that as well. And then of course, given that the number of moles of potassium hydroxide are added to 225 milliliters of this buffer, what is the pH of the resulting solution? Assume that the volume does not change upon adding potassium hydroxide. Okay, so of course that is a very basic term and very key. We are told a buffer, so there is addition of potassium hydroxide to our buffer. So what is the buffer solution that we are talking about? So a buffer solution that we're talking about is that So we have KH carbonate, and then you have sodium 2 carbonate as well. Okay, so from my understanding, this is our acid, and of course after dissociation what we expect is we have our proton there, and then what else do we have? So we have that remaining. We can write this. So we have K carbonate, something like that. Now what's basically happening again is we have sodium 2 carbonate. So this potassium can actually even go, so that you have sodium 2 carbonate, and then of course plus the potassium there, and then of course you get to add potassium hydroxide and whatnot. But the basic idea is this is our acid. Just take note that is our acid, and then of course this is like our salt. Okay, and then of course you can think of it to be our conjugate base as well, so that you just understand where we are getting to go with our equation. So what they want us to do is they want us to find the pH in this case. So how do we get to find the pH? So looking at what we have, the basic acid itself, if you think of it, forget about the potassium that we have that is being indicated. So just like I mentioned, our acid is hydrogen carbonate, and then of course after dissociation what we have? We have this losing what? Losing the hydrogen, so that you get to have just your carbonate. Okay, so this is very, very important for you to understand. So this is our acid, and then this is our conjugate base. So we've ignored the metals, of course, and then if you look at the information that we've been given, we've been taught to say that is 0.384 molar concentration, and then this is 0.239 molar concentration. So what are we talking about now? What is our volume in this case? So the fact that we're not given any information about our volume, and then we've been given molar concentration, we can consider to say our initial volume was what? Let's say a liter. So if our initial volume was a liter, what it means is if you try to determine the number of moles, so you do know that your concentration is equal to number of moles over volume, and then if you consider your volume to be 1 liter, and then you do expect that, okay, well, if my volume is a liter, then I expect that my molar concentration is basically going to be equivalent to what? To the number of moles, because volume is equal to a single liter. So therefore in this case I can just convert these to moles. Okay, so that is in moles, considering a volume of a liter. Okay, so those are the number of moles that we have initially. Okay, now what is the question saying? If 0.0464 moles of potassium hydroxide are added to 225 milliliters of this buffer, so basically the volume, it wasn't even necessary of us to even take this to moles, because actually the volume has been given of this buffer. It is 225 milliliters instead of what we are talking about. Okay, so let's just maintain our concentrations there. So molar concentrations. So I'll not edit that because I want you to understand how you get to approach some questions in real life situations. Okay, so you've actually gotten that point to say we have our molar concentrations to be the units of our concentrations as indicated, and of course we've now been taught to say the volume of 225. So if we have 225 milliliters, that's the same as 10 to the power negative 3 liters. So we should be able to find the number of moles of these two. So starting with our acid, we do understand that number of moles is a product of concentration and volume. And of course, the reason of us converting to liters is because we have molar concentration. So what happens if you get to multiply the two? your concentration against your volume. That is of course going to give us 0.0864 moles. And then if you go to the other part, you also do the same, trying to determine the number of moles of our conjugate base. We have something like 0.053775 moles. So we now have our number of moles for both the acid as well as the conjugate acid. Okay. Now, the addition of 0.0464 moles of potassium hydroxide, what effect does it have? So looking at the potassium hydroxide, if you write potassium hydroxide. So potassium hydroxide, from what it sounds, this is basically a base, right? Because it's an hydroxide. So we do expect that to react with what? We do expect that to react with our acid. In this case, the acid that we have is going to react with that. Okay, we can now try to come up with an equation there to just show the reaction. So our hydrogen carbonate, therefore, which is being our acid in this case, the fact that we're adding a base is going to react. Okay. So if this gets to react, what do you expect to be produced? Of course, that is an acid. So an acid is expected to lose a, so that it will be potassium carbonate. So this is going to react with that potassium carbonate, and then you are also going to have plus the hydroxide is going to react with that. So hydrogen. So what is going to be hydroxide plus the H is going to give us water. So this is a neutralization reaction where we have a salt forming and then also water being formed. Now, I just wanted to write these equations to just show what is basically happening in this case. What is happening is this. This base that we are adding to our solution, which is potassium hydroxide, is basically reducing what? Is basically reducing our acids. Why? Because it's neutralizing the acid and then leading to the formation of what? Formation of water. But not only is that happening, what else is happening? We are also increasing the carbonate in concentration. Just like we've seen, calcium carbonate is going to increase in the solution. So therefore, we are leading to an increase in our conjugate base in the solution. Okay. Now, looking at the equations that we've written, these are just basically in the ratios of 1 to 1. Okay. So therefore, the number of moles of potassium hydroxide that were made available in our reaction is basically equivalent to the number of moles of the hydrogen carbonate that reacted with it. And then of course equivalent to the number of moles that were increased to our conjugate base. That's the basic idea. That's why I wrote the equation to just demonstrate that. So therefore, the fact that we are adding a base, it is going to reduce the number of moles of what? Of our hydrogen carbonate, which is an acid, because those two, of course, are supposed to react together. And of course, from our equations, they are in the ratio of 1 to 1. So we expect an equivalent number of moles to be lost from our acid because they are supposed to react together. So I'll subtract from our acid, and then I'll add to our conjugate base, because from our equation we're able to see that there is an increase of calcium carbonate in our solution, which is increasing the carbonate in the solution. Of course, an equivalent number of moles which is being lost from the acid is what is going to be gained on the conjugate base. So this is like the funny part about these buffer solutions. It's like whatever is being lost is being gained by the other. So that's why there are minimal changes or reductions in terms of the pH. So if you get to subtract there, you have 0.04 moles, and then there you have 0.100175. So at this point now you can agree with me that we now have a number of moles of our hydrogen carbonate even after adding what we had added to what we have. Okay, so now what are we supposed to do first now to get to find I can now erase this. And of course I just need to write that this is basically denoting our acid, hydrogen carbonate, and then that is denoting our conjugate. So I'll say our carbonate, our conjugate base. Okay, so those are the final number of moles that we have on both ends. And then of course if you go to our equation is that the pH is basically dependent on pKa plus the log of what? So of course we said the conjugate base over the acid, sorry, not the conjugate acid, but the acid itself. So pKa of course is the negative log of what? Is the negative log of Ka. So K is basically the constant of dissociation, which is basically the given value. That is the constant that was supposed to be given in the question. And of course we need to know that the Ka for our acid, which is hydrogen carbonate in this case, is basically 4.7 times 10 to the power negative 11. That is our Ka for this acid that we have. So we can substitute in the equation negative log of 4.7 times 10 to the power negative 11, and then plus log of what? Look at our base now. Our conjugate base in this case, we had an increase in the concentration which gave us that. So I'll say 0.100, and then I'll divide by our acid which was 0.04. So you can basically grab your calculator there and perform our calculations that we get to see the pH that we're basically going to have. So we have 10.328 plus 0.398 giving us 10.726 as our pH. Okay, so in summary, what was basically important for us to identify from our question was identifying first of all which one is an acid, which one is our base, of course our conjugate base, which is that one, and then of course trying to understand the effect of what we are adding. The fact that we are adding an hydroxide, which is basically a strong base, is supposed to react with our acid in this case, which is that one. Therefore that led to a reduction in the concentration of our acid, and of course led to an increase in the conjugate base. Okay, and also we have this value had increased and then the other value had reduced. So it's very important. Those are very simple steps, and of course get to know the Anderson equation, because it's going to be very helpful in a case where they've given you a buffer solution and then they expect you to get to find the pH. Okay, so that's it for this video. I hope that you now have a basic understanding of what